Hello once again, class, and welcome to another mock lecture. Today, we finally get to tackle optimization. Ladies and gentlemen, we made it. We finally know enough about finding extrema to talk about the application of optimization. And that means tackling stuff like minimizing cost, maximizing profit, maximizing area or volume given a fixed amount of material, and this is kind of what I'm going to focus on for the two examples that I have for you today. But you can also do other stuff with optimization. Anything that needs maximizing or minimizing. This is an application of finding extrema. Now, the strategy that we generally want to use for these types of examples there's like 7 steps, which sounds like a lot, but I think a lot of this is just approaching word problems in general. Like, these are things that you would want to do when you're approaching any kind of application question. And the first is, what are you trying to find out? After you've read the paragraph of information that's describing what's going on, ask yourself, what am I ultimately trying to do in this example? Second thing you want to do is you want to visualize what it is that you're being asked. If it's maximizing an area, then you should draw that shape and give variable names to width and height and whatever else there is that's involved. If it's volume, similar thing. If it's a cost function that you're trying to maximize, let's figure out what that cost function looks like. And that is part of the third thing that you're going to do, which is you need to assign some variables. And this is going to be different for every different type of optimization problem that you run into. But ultimately, there is going to be one thing that you do want to optimize, which is to say there's one thing in particular that you want to maximize or minimize. And for the sake of giving it a name for the rest of the steps, in this strategy, we're going to just call that M. Right, that's the thing that we want to maximize or minimize. But give names to other quantities as well. Like before I had said, if there's a length, then let's make that L. Right, if there's a height, then let's make that H. Give your variables meaning. That way when you're looking at them, you have an idea of what that's supposed to be. The next thing we want to do is we want to write M in terms of whatever the other variables are, just so that we have an equation that we can point to and say, hey, this is M, this is the thing that we want to try to maximize, which means, of course, finding your critical points by looking at where the first derivative is 0, checking to see where max and mins lie, checking your endpoints, normal maximization, minimization stuff. But we're going to need an equation that we can point to and say, hey, this is the thing that we want to do that thing for. And sometimes your equation is going to be in more than one variable. You're going to have more than one independent variable. And we don't know how to maximize or minimize stuff like that. So we need to somehow write it in terms of only one of the other variables. And we're going to go through a strategy for how we can do that. But once you get to step 5, you should have an equation that we can say, hey, just maximize this thing. And that's what you want to do. Find the absolute min and max at this point. If the domain's a closed interval, don't forget to use your endpoints, because ultimately we're finding absolute extrema when we're doing this stuff. You want to find the highest or lowest value. And that's it. I think I said 7 steps before, but clearly here I have 6 that are listed. But again, I think like most of this, at least the first 2, like definitely the first 2, and maybe you can argue the first 3 and potentially 4 if you're working with more than one variable as an independent variable. Like most of this stuff is just, here's how you approach problems in general, right? The only kind of application for maximization is really the last step, right? Find your min and max once you've got only just one variable, one independent variable, I should say. So with that out of the way, we're going to apply this strategy to 2 examples. In example number 1, we're going to suppose that a farmer wants to enclose a rectangular field for his horse. He has 2,400 feet of material and decides to use a straight part of a nearby river as one of the sides. What dimensions produce the largest area for his horse? All right, so the first thing that we should do is I'm going to draw a picture. Right, I guess I should backtrack. The first thing is, what are we trying to do? And in this case, we're trying to figure out the dimensions that produce the largest area. Which is to say, we need to find the width and length that give us the largest area that's enclosed by those things. The kind of interesting part about this word problem, because you might say, well, a square just maximizes area. The thing that makes the answer not a square in this example is the fact that we only need to construct one length and 2 widths. Right? One of the lengths is going to be taken up by a river. Now you might say, well, hold on, Mock, why can't width be the river? Well, if we're trying to maximize the area, then we should have the longest side be taken up by the river, right? Then we're able to use more material for the width than we otherwise would for the length if we were to use the river for the width. All right, but we are trying to maximize the area here. So let's get some important formulas written down. We're maximizing area, which means we're going to use the area formula. Area is equal to length times width. That's the thing I want to maximize. The problem, though, is that it's in two variables. It's in length. It's in terms of length and width. We also have the perimeter formula at our disposal. Since we know that we're given this much material, we're going to have to use the perimeter formula to kind of divvy up, if you will, that material for the two widths that we have to construct as well as the length. And so perimeter is equal to 2W plus L, which means 2W plus L is equal to 2,400, right? Feet of material. Let's just say it's fencing. All right, well, from this formula, what I can do is I can actually solve for L. All I'd need to do is subtract 2W from both sides. And now look, we have L in terms of W. So what I can do is I can take that formula for L and plug it into the area formula for L, which means that our area formula now is only in terms of W. And so I renamed it A of W to kind of, I guess, really point out that, hey, this is the area in terms of only the width. But we get negative 2W squared plus 2,400W, and that is a quadratic, and I can maximize that thing. At this point, we just need to maximize it. It's going to look something like this. It's opening down because its leading coefficient is negative, and it has one vertex, as most parabolas do. Really, all parabolas have just one vertex. Anyway. Now, I did actually solve for the x-intercepts of this parabola because I wanted to establish myself a domain for where this makes sense. Obviously, we can't have a width that's negative, so 0, I guess, is what's gonna be counted as our lowest point, and then solving the other way. And by the way that I solved is when I set this equal to 0, I just factored out a negative 2W. So that's where I got the 0 from, and then from here we get 1200 as the upper bound. So I said let's just say that's a closed interval. We don't really need to work with it, and honestly, you could even argue, shouldn't that really be an open interval because you can't have a width of 0 either. Even plugging them in though, right, A of 0 is equal to A of 1200, which is, they're both 0. So even though we should still calculate them along with the critical point that we find for this thing, which is going to be where our derivative is 0, those aren't going to be the absolute maximums. They both give us 0. So now we need to actually find the maximum, which means we need to take the first derivative. Here is where I'm finding my critical points. First derivative is negative 4W plus 2,400. That is just power rule stuff that's happening there. If you set it equal to 0, you just get 600. First you subtract 2,400. You divide both sides by negative 4. You get that the width is 600 feet. And that is actually going to be what our maximum is. Here's me plugging them in again, the endpoints that is, along with the critical point, and very clearly the maximum comes from when the width is 600. All right, so our width is 600, which means that if you plug that 600 back into this equation here, right, so 600 in for that W, you get 2,400 minus 2 times 600, which is 2,400 minus 1,200, which is 1,200. So the length is 1,200 feet. So in fact, this is a rectangle whose length is twice the width. And that gives us the maximum area. By the way, in case you're wondering, and it doesn't really ask, but the max area would be 720,000 square feet. All right, example 2. A cylindrical can needs to hold 350 cubic centimeters of liquid. Find the dimensions that will minimize the amount of material used in the construction. So just like last time, we're trying to find dimensions. In this case, we're trying to minimize it. By the way, 350 cubic centimeters is approximately 12 fluid ounces. It's like a little bit less than 12 fluid ounces, but this is just your typical can of soda, basically. What are the dimensions that produce a can that uses the least amount of aluminum? That's basically what this question is. So again, what we're trying to find is minimizing the dimensions, which means we need a height and we need a radius. Those are the main dimension components of a cylinder. Because we're trying to minimize the amount of material that's used in the construction, fundamentally, we're talking about the surface area of the can itself. How do we minimize the amount of material that folds into this can, basically? And a can has a top and a bottom, both of which are circles, and then the vertical part of the can itself is comprised by the height and an unfolded top and bottom, right? Circumference. So you have a rectangle that is 2 pi r times h in area here. And then, of course, the two circles are both pi r squared. There's 2 of those. So the surface area formula for a cylinder is 2 pi r squared plus 2 pi r h. Pi r squared here, pi r squared here, pi r h here. That's the thing we are trying to minimize. But just like the last problem, this is in two independent variables. It's in terms of two independent variables. There's radius and height. Now, we're given a specific volume that it needs to hold, so we should also talk about the volume formula. The volume formula is pi r squared times the height, right? It's the area of the base multiplied by the height of the can itself. And because we know what the volume is supposed to be equal to, which is 350 cubic centimeters, we can use this information to actually solve for h so that our area formula will only be in terms of radius. So let's do that. What I did is I just divided by pi r squared. That's actually it. So then I just plug that in for the h that exists in the area formula, and now we have the area in terms of r. So this is the area formula in terms of only a radius, and it's 2 pi r squared plus 2 pi r times 350 divided by pi r squared. I should also mention, like, this is not a general formula for area in terms of radius alone, right? That's going to depend on what the volume is, right? We had to use the volume equation to figure out what h was. Otherwise, this would just say v, and that wouldn't really be helpful. Because we know the volume we're trying to construct, that's why this is now only in one variable, that one variable being r. This formula, by the way, can be simplified. Like, notice there's an r in the numerator. I said r and underlined pi. Nice. There's an r in the numerator. There's also an r in the denominator. There's an r squared. There is pi's in numerator, denominator as well. So some stuff's going to cancel here, and this is going to reduce to 2 pi r squared plus 700 over r. And that is the thing we want to minimize. Okay, so let's go ahead and differentiate, right? Oh, also, I put on here the domain of this thing, just like the last one, you can't have a height of 0. It wouldn't hold any liquid, right? A height of 0 would not hold liquid 350 cubic centimeters. And that's why I made this one an open endpoint at 0 instead of closed like last time. But then I guess theoretically you could have a height that goes to whatever we want. The height could be 0.00000000001, and it could still hold 350 cubic centimeters as long as it had a wide enough radius. So I made it infinity as the upper bound, which is to say that there isn't an upper bound, but like in a practical sense, there's an upper bound. Theoretically, though, it's infinity, so I just left it as infinity. So we're not on a closed interval in this situation, which means we can't just use the closed interval method and find the highest value and say, hey, that's the absolute maximum. At best, we're finding the local maximum, but there's a way around this that we'll get into a little bit later. Anyway, I'm going to go ahead and now find the critical points of this thing. So I found the derivative to be 4 pi r minus 700 over r squared. That's by power rule, kind of in both parts, right? Power rule, bring down the 2 here, that becomes 4 pi r. 700 over r is really 700 times r to the minus 1, so the minus 1 comes out in front, that's why this is minus. And then this becomes minus 2 as a power, but I just left it in the denominator. So here we go. Here is our derivative. I also actually combined the fractions in this case, just to make it easier when we're solving for the critical points. To figure out where this thing is equal to 0, the first thing that I would do is multiply by the denominator, and that's why I combined them. And it turns out you just actually only care about when the numerator is 0 when you're doing this. So we get 0 is equal to 4 pi r cubed minus 700. I added 700 divided by 4, which 700 divided by 4 is 175, divided by pi, and then took the cube root of that whole thing, and that's the radius. Which I used a calculator just to give this a little bit more tangibility, if you will. It turns out it's about 3.82. It is in centimeters. I don't know why I did not include my units there. I should have really done that. It's 3.82 centimeters, and I know that it's in centimeters because the volume that's given is in cubic centimeters. So that is actually our only critical point. To which you might say, well, now hold on a second. What about 0 as a critical point? 0 makes this thing undefined, and critical points are literally defined to be points that make the derivative 0 or undefined. And 0 clearly makes this thing undefined. It gives you 0 in the denominator. But remember that our domain is on the open interval 0 to infinity. So 0 is actually not even in the domain. So we don't need to worry about it. So here's our sign analysis. We're finding the extrema. I'm using the first derivative test, really because I don't really want to differentiate this and use the second derivative test. The second derivative test will still give you that this is a minimum, though. But the first derivative test, a little bit more clear. My test value between 0 and 3.82 centimeters was 1. And I got this thing here, which is 4 pi minus 700. That's very clearly a negative. So I put negative here. And then my test value past 3.82 was 1,000,000. And a prime of 1,000,000 is a really big number minus a really small number. So it's positive. So by the first derivative test, we can conclude that 3.82 is a minimum. And so that's it, right? Our radius, right? The dimensions that will minimize the amount of material used in this construction. Here's one of them. The radius is 3.82 centimeters. The height, you could figure out by just plugging it into the height formula that we had found before, which was 350 divided by pi r squared. Okay, so let's just do that, right? The radius is, and I'm about to find the exact value. That's why here, trying to be as precise as possible, I didn't use this. I used the cube root of 175 over pi. You end up getting that it's twice the radius. That's basically what it ends up being. You can pause here and see all my work to explain how I got there. But basically, by just doing some algebra, I found out that the height is literally twice the radius. This is the radius that we found already. That's 3.82 or whatever. So that means that our height is twice that amount, which is approximately 7.64 centimeters. All right, and then we're done. That minimizes the material, which therefore will minimize the cost, right, of this thing. Now you might be wondering, hold on a second, the first derivative test only finds local extrema, and yet I just concluded that it was an absolute minimum, right? I just said, okay, well, that's the smallest value that appears, so I'm done. Well, that's true. That's a really good point. It's a good thing that the first derivative test for absolute extrema values exists, though. And all it says is that suppose that c is a critical number for a continuous function f defined on some interval. If your derivative is positive for everything before the c value, and your derivative is negative for everything after the c value, then you're allowed to conclude that f of c is actually the absolute maximum. In this picture, in both of them actually, the purple line is f prime. So notice that the derivative is above the x-axis, then c happens, then it's below the x-axis. And that corresponds to my base function looking something like this parabola here. You know, because it's increasing, then c happens, then it's decreasing. If that's the case, then actually that thing is going to be the absolute maximum. Basically what this theorem is saying is, hey, if these are arrows, right, and that goes on forever, then that one maximum you found is actually the absolute maximum. And the same thing can actually be said for the minimum. It says if your derivative is negative for everything before c, so it's all negative before c, then it's positive for everything after c, so all these x values give us positive, right, y values, then f of c is the minimum, right, in that case. By the way, if you're wondering, all of these upside down capital A's, I don't know if I've actually said this in any of the videos. That means for all. So for all x less than c, and f prime of x less than 0 for all x greater than c, right? That's how I would read that statement right there. But anyway, here's our example. It actually falls into the criteria for the first derivative test for absolute extrema, because for everything in the domain, which is from 0 to infinity, that's an arrow, it's negative before the critical point and positive for everything after the critical point. That's this situation. So therefore, by the first derivative test for absolute extrema values, it's the absolute minimum. So that's it. Hopefully that was helpful. Hopefully you guys learned something. If you have any questions, please send me an email or drop a comment below. Thanks a ton for watching, and I'll see you in the next one.